Welcome. It's time to talk about the hyperbolic plane. Before we do this, I want to put this in context of the geometries we studied so far, namely the Euclidean geometry and the spherical geometry. So let's just make a quick reminder of these other geometries. So we studied the Euclidean plane. And even though we never introduced any coordinates in the Euclidean plane, it is really the same if we do study the classical Euclidean plane using the Cartesian coordinates x and y. So Euclidean plane is, in this realization, just a standard R2, standard xy plane. And then the distance or the length of any curve, right? If I draw any curve on the Euclidean plane, starting at point P and Q, and this curve is given by a parametric equation. So Euclidean plane, our notation for Euclidean plane was this. So if this is a curve, which means in particular it's a smooth function, so has all the derivatives, then such that C of A is P and C of B is Q, then the length of C is the integral from A to B of the square root of dx over dt squared plus dy over dt squared dt. Sometimes this thing that's here under the square root is called the Euclidean metric. Of course, we derived this in one of the videos, and you remember that this really comes from dividing the curve into small pieces and then using the Pythagorean theorem on each of the small pieces. What do the geodesics on the plane look like? They're just straight lines. So if I want a geodesic between point A and B, that's just a straight line segment. So geodesics are straight lines, or line segments if you specify 2 points. So that was the Euclidean plane. The next thing that we studied was the sphere. And in fact, I want to actually keep this somewhere on the board. So I'm just gonna make a little note here. So Euclidean plane E2, length of curve, is given by the integral from A to B, the square root of dx over dt squared plus dy over dt squared dt. So the next thing that we studied was a sphere. And last time when we talked about people who live in the flatland, we talked about how to represent a sphere on the plane and then how to explain to people who could never imagine the third dimension what a sphere is. A way to explain it is by distorting certain distances on the plane. So what was the planar model for the sphere? It was part of a plane. Sphere is sort of a finite concept, so that's why it wasn't the entire plane, but it was part of a plane. Here, so I put the spherical coordinates here, and phi was pointing down, while theta was pointing to the right. Why is phi pointing down? Well, that's just a convention, because phi is the angle between the line that connects the center of the sphere with the North Pole, and another and the line given by the center of the sphere and the point on the sphere. So it's that angle rather than that angle here. So as you move down with the point, the angle increases. So that's why I drew my line, my axis here, but I could have just reversed it, and this would then be sort of the south pole would be here and the north pole would be here. Okay, and then this went from 0 to 2 pi here, and on the phi axis from 0 to pi there was the equator somewhere in the middle, so that was phi equal to pi halves, equator. Then we sort of ran an experiment when we took phi equal to pi over 6. We had this other line here, and we were trying to compute, we also did some vertical lines. So this was theta equal to pi halves. This was theta equal to pi. And we, for example, we computed the lengths of the sides of this rectangle here, A, B, C, D. Well, what looks like a rectangle on this planar representation of the sphere is actually not a rectangle on the sphere. So this length, because the metric on the sphere does not distort the distances on the equator, this was just pi halves. These were here the difference between pi halves and pi 6, so they were pi thirds. Again, no distortion of the distance in the vertical coordinate, but here in the horizontal direction, away from the equator, there was distortion, and this was actually only pi fourths. Okay, we did these calculations in the previous video. And in fact, we got a formula, general formula for the distance on the sphere, which was like this. So it was the integral. So if I give myself any curve, C again P here, Q here, and the C is such that, so C is a curve from AB into S2, C of A is P, and C of B is Q. Then the length of this curve in spherical coordinates is equal to the integral from A to B, the square root of d phi over dt squared plus sine squared phi d theta over dt squared dt. So that was the length of the curve on the sphere. And in fact, the situation here was sort of twofold. Us, who can understand the third dimension, can actually imagine sphere this way, the way it actually is, and then we don't have to distort any distances. That is, the distances on this is the real sphere. So the distances on the sphere are what they are. They are just lengths of geodesics, so they are length of arcs of great circles. However, for those creatures who cannot comprehend third dimension, they have this model. We would tell them the sphere is actually this rectangle, this part of a plane, and you define this strange distance on it. To make it even look more like this, I'm going to now rename these coordinates, and I'm not going to call them theta and phi, but instead I'm going to just call them x and y. X sort of the horizontal one and y the vertical one. Well, that's sort of how people who live in two dimensions will probably just think about these things. So then I'll get, sphere, I get the length of a curve on the sphere is the integral from A to B, the square root of, okay, so I denoted now phi by y and theta by x. So let's just in symmetry with this, let's put the derivative of x with respect to t first. So that's going to be sine squared of y, remember phi is y now, dx over dt. squared plus dy over dt squared dt. Okay, so in this sense, you can now represent the sphere and the Euclidean plane on sort of the same picture, almost, as Euclidean plane is the entire plane with this distance, with this length of curves, and sphere is that bit of a plane with this distance or length of curves. And finally, what were the geodesics on the sphere? Well, all the vertical ones are sort of half circles, right? All of these represent these great circles that connect the North Pole with the South Pole. This one is here, that's the equator. But if I want to draw some other great circle that sort of goes like this, then I'm really bad at this. Okay, here's another great circle. So you see it intersects the equator and then goes above the equator, and on the other side it goes below. So it's something like that. Okay, and as you move this further and further towards something that looks more vertical, these geodesics start looking more like this. And of course, if you want then the shortest distance between any 2 points, it's like whatever this geodesic is here. It's kind of easier to find on the actual sphere than it is on the model. The equations on the model are more complicated. Okay, so let's move now to the hyperbolic plane. And I really want you to keep in mind this dichotomy we had for the sphere. We had the actual sphere, and then we had its representation on the plane. You cannot really flatten the sphere onto the plane without distorting distances, so we flatten it with distorting distances. And when we describe how we distort the distances, we can just say that that plane with those distorted distances, with this metric, gives you a representation of a sphere. So what is a hyperbolic plane? Now we will be like these people in the flatland. It is really not quite possible for me to draw a representation or hyperbolic plane in the 3 dimensions that I have at my disposal in my world or in your world. All I can do is to draw a planar representation of the hyperbolic plane. Okay, so hyperbolic plane is actually also can be thought of as part of a plane, but only its upper half. So planar model of the hyperbolic plane consists of the subset of R2 where y is strictly greater than 0. That means the x-axis is not part of the hyperbolic plane, only what's above the x-axis. And then I have to tell you how to measure distances on the plane, on this hyperbolic plane. So, hyperbolic plane I define the length of curve to be the integral from a to b, the square root of dx over dt squared divided by y squared plus dy over dt squared divided by y squared dt. Okay, so look, we now defined 3 different metrics on the plane or on parts of the plane. This is the Euclidean metric, this is the spherical metric, and this is the hyperbolic metric. For this doesn't distort any distances, So the plane is what it is. What we see, the Euclidean plane, it's also planar representation. For the sphere, if you think of a sphere as this rectangle on the plane, you can think about it this way, and then this is the metric on it. A better way to think about it is as an actual sphere, because then we have a much better idea of what it is. For the hyperbolic plane, if you want to think about its planar representation, then that's just the upper half plane, and this is the distances, this is the metric. What is a hyperbolic plane in reality? I cannot draw a picture for you. There are ways to imagine this. I'll give you some ideas later, but in general, it's not like with the sphere, that here in R3 I have some sort of surface that I can say, oh, this is the hyperbolic plane, and this is just its representation. Okay? It's not so easy to imagine what a hyperbolic plane is. I just want you to notice that this integral can be simplified. I mean, I can take the y squared outside of the radical, and so it's just this. All right, but it's kind of, last time let me say about this, there's this trichotomy here. For the Euclidean plane, we had a plane, we didn't need a model. For the sphere, we had the sphere, and we also had the planar model, just in case somebody cannot understand the third dimension, or if you need a map or something, then you don't usually carry a globe with you. You carry this flat representation of it. For the hyperbolic plane, all we're going to be working with is that representation. And this actual hyperbolic plane, it will be somewhere there, and it would be trying to imagine how it looks like, but I can't just like give it to you and say, okay, this is like, I could give to you an apple or a sphere, a ball, a globe, and say, oh, this is a sphere. I cannot really do this with the hyperbolic plane. All I have is this planar representation. So let's see what happens with how the various distances look like on the hyperbolic plane. So let's look at some points here. So maybe 1, 2, 1. Okay? So let's try to actually measure. Let's actually look at maybe 2 squares here. This 1 somehow came up too high. Okay? So I'll call this A, B, C, D. All right, let's look at this square first, because that one is somehow suspicious, because its vertices lie on the x-axis, and the x-axis is not part of the hyperbolic plane. So you might think, what happens there? As the people approach the x-axis on the hyperbolic plane, do they just like see that the world suddenly ends? Well, let's first deal with this. Okay, let's compute the various lengths. So first the AB. So I don't want to say that this is the distance between AB, so I'm just going to take a curve, and I'm going to, again, parameterize it the simplest way possible. So because I want to go from A to B, I'm going to parameterize it as going from 0 to 1 into the hyperbolic plane. Let's define it C of t to be, okay, so the x coordinate goes from 0 to 1, so that's just t, and the y coordinate stays equal to 1. Then what's the length of this curve? So that's the integral from 0 to, let's compute the derivatives first before we do the integral like we did last time. All right, so dx over dt, x is equal to t, so that's just 1. And dy over dt, well, y is constant, that's 1. So this dy over dt is just 0. Okay? So what we get is that the distance, the length of the curve, is the integral from 0 to 1. So dx over dt is 1. So this the whole thing underneath the square root is equal to 1. So, and y, what about y? Y is also equal to 1, right? So y in this formula is also equal to 1. So I just get the integral of dt. So that's just 1. So this line, this length here is 1. Just like on the Euclidean plane. And note, look at this formula. When y is equal to 1, so we are on this line here, y is equal to 1, then this formula becomes the Euclidean formula. There are no distortion of distances if we are on the line y equals 1. So no distortion of distance. That is, the distance is the Euclidean distance. So you can now tell me what's the distance between the point 1, 1 and the point 5, 1. Well, that's just distance is 4. 5 minus 1. But let's see what happens on this line segment DC here. So again, I reparameterize my curve. So now I want it to go from D to C. So what's the change in the formula? The only change is that the y-coordinate becomes a 2, right? So as t goes from 0 to 1, the x-coordinate goes from 0 to 1, and the y-coordinate stays 2. So what's the length? So I need to compute all the derivatives. So dx over dt, that's still 1. And dy over dt, well, that's still 0. Except the only difference is that now y is 2. So the length of the curve is the integral from 0 to 1. This entire thing is now 1. And now the bottom of it becomes 2. So that's just 1/2. So this length is 1/2. So as you move up, the horizontal lengths become smaller. Let's then try to compute the vertical distances here. So let's compute the distance between point A and point D. Well, that's not the distance. I'm sorry, I keep saying distance. I'm not claiming that these line segments are geodesics. Okay, maybe these are not really very good curves in the sense they're not geodesic curves. It was the same thing with the thing that looked like a spherical square on this planar representation of a sphere. The part on the equator was actually a straight line because that was a geodesic, but the other part, when phi was equal to pi over 6, was not a geodesic. Right? So I'm not claiming that these are geodesics. But so let's now parameterize a curve C of t so again, I'm going to go from, well, what's the simplest thing here? If I'm going from here to here, I'm just going to go from 1 to 2. So 1, 2 into the hyperbolic plane. So I'm going to define C of t to be, okay, so now x is 0 and y is t. So I'm going from here to here. Okay, so now I'm computing dx over dt, that's 0, and dy over dt is equal to 1. So if I do that, what is y? Oh, y is equal to t this time. Right, this is y. So my integral becomes the integral from 1 to 2. So what do I have in the numerator under the square root? Well, the dx over dt is 0 and this is 1, so I just have the square root of 1. So I get 1 divided by and y is t dt. Oh, okay, so that's natural log of 2 minus natural log of 1. So that's natural log of 2. That's interesting. So this length here is actually equal to natural log of 2. What about that length? Let's try to do that as well. So in this case, I am going to change this 0 to a 1, and everything else stays the same. And let's see if anything changes here. So dx over dt is still 0, dy over dt is still 1, and y is still equal to t, so nothing changes. So this is still natural log of 2. Okay, now let's look at this rectangle here. This side I already know, it's 1. This side I'm not going to compute because that part is not in the hyperbolic plane. So I wonder, like, what is that distance here? Not distance, I keep saying distance. What is the length of that curve here? So I'm going to write this vertex here as E, and this one as F. But remember, the vertices E and F do not lie on the hyperbolic plane. They're not part of it. But I can compute the distance, so that means I can compute what happens as I approach them. Not the distance, I'm sorry, the length of the curve. So I now parameterize my curve this way. So I go from 0 to 1. Oh, but I do not include 0. So it's an open-ended interval from 0 to 1 into the hyperbolic plane, where I say c of t is, okay, so the x is going to be 0, but the y is going to be t, right? So I sort of go from here to here. So dx over dt, well, that's 0, and dy over dt, that's 1, and y is equal to t. So everything is the same as just in this previous example, as I was trying to compute this length. But let's actually do the calculation. So what do I get here? So I get L of c, that's the integral from 0 to 1, 1 over t dt, right? Dx over dt being 0 and dy over dt being 1 gives you the numerator still 0, and y being equal to t gives you that bottom here. Oh, but that's an improper integral, right? I mean, because at 0 this function is undefined, and that actually does make sense because that point is not there. So that's the limit as b goes to 0 of the integral from b to 1, 1 over t dt. So I'm going to continue this integral down here. So what do I get? So that's the limit as b goes to 0 from the right. The integral is natural log of t between 1 and b. So that's the limit as b goes to 0 from the right of natural log of 1 minus natural log of b. Now, natural log of 1 is 0, so this is just the limit of natural log of b. But what's the graph of natural log? Natural log looks like this.